Hi, today I'm going to show you how to implement a high-side current sensing solution using comparators from Texas Instruments. In industrial applications such as motor drives or factory automation, it's important to make sure your load doesn't draw more current than it can handle. Comparators can offer a simple, cost-effective, and compact solution for these applications. For more resources on this application, please visit ti.com/comparators. Let's get into it. Our comparators are super simple, discrete, and a cost-effective solution for overcurrent sensing. Comparators are also faster and more precise than other current sensing techniques such as fuses or integrated current monitors. Now, why would we want a solution with faster speed? When an overcurrent condition is present, it could potentially damage downstream circuitry. A faster comparator can help with the solution by responding to the event quicker. To design a high-side current sensing solution with a comparator, you should keep in mind these 3 design notes. Use rail-to-rail inputs, have an open drain output, and be sure to have a low input offset. Now, the reason you want rail-to-rail inputs on your comparator is because the voltage that it will be sensing will be very close to its high-side supply. The reason why you want low input offset is to maximize the accuracy of your circuit. Now, because this is high-side current sensing, our comparator will be powered off the main 12-volt supply. Lastly, we want to have open drain outputs on our comparator. Because we are doing high-side current sensing, our comparator will be supplied off the high-side voltage supply. So you don't want your output to carry the high voltage downstream to your more sensitive devices, such as an MCU. An open drain output allows you to level shift the output down to a lower voltage level to protect your downstream circuitry. Today, we will be using the TLV1701 to create our high-side current sensing circuit. The TLV1701 features an open drain output, rail-to-rail inputs, and a low input offset, which matches all the criteria we discussed previously to create a high-side current sensing application. Even though we are creating the circuit for current sensing, comparators can only detect a voltage for which to respond. We can use a shunt resistor between the voltage source and the load to translate the current into a voltage. The voltage across the shunt resistor should be at least 10 times greater than the comparator's input offset voltage. This is so that the input offset of the comparator does not interfere with the amount of voltage sensed from the shunt. Otherwise, the circuit would be less precise. Here, we'll define the overcurrent threshold to be 1 amp and R shunt to be 100 milliohms. This would satisfy the condition that V shunt is at least 10 times greater than the TLV1701's input offset voltage of 5.5 millivolts. Next, we need to convert our overcurrent threshold of 1 amp into a voltage that the comparator can use as its reference. In an overcurrent condition where the load current is 1 amp, the potential at the load should be 11.9 volts, which is the voltage we will apply to the comparator's inverting terminal. Now, how do we apply the 11.9 volts to the inverting terminal? We can actually accomplish this with a simple resistor divider. As a quick refresh, the output voltage of a resistor divider is equal to the voltage source times R2 over R1 plus R2. So we know our voltage source is 12 volts, which leaves us with 2 unknowns. We can assume a resistor value for R2, let's say 1 megaohm, which leaves us to solve for R1. R1 in this case is approximately 8.4 kiloohms. So now that we have solved for R1 and R2, we can finish building our circuit. We have now completed designing our high-side current sensing circuit. Now let's go build it on the bench. Now that we have built our circuit, let's go test out our design. So the load and the comparator will both share a 12-volt supply, and the output of the comparator will be level shifted to 3.3 volts. And I actually have a second power supply here to differentiate how much current the load is drawing versus how much current the comparator is drawing itself. So as a reminder, we set up our comparator in an inverting configuration. That means the output of the comparator will stay high under normal conditions when there is not an overcurrent condition present. If we were to force the load to draw more current than 1 amp, let's say 1.2 amps here, then we should expect the output of the comparator to go low, which it does here. So that's how you design a high-side overcurrent sensing solution using a comparator. For more information and resources on comparators, please visit ti.com/comparators. Thanks for watching.